The team lives by the motto, today, tomorrow, forever. Today is everything we do to prepare for competition. It's the blood, the sweat, and the tears that goes into our project. Tomorrow is our commitment to our members. We're not just building a rover. We're building better engineers, better scientists, better managers, better leaders. Forever is our commitment to the future, to creating a lasting impact and inspiring the next generation of STEM students.
And now it is my honor to present to you our 2016 Rover, Zenith.
Welcome back to Missouri University of Science and Technology. My name is Alyssa McCarthy, and this is the Mars Rover Design Team.
This year we've tried to reevaluate every part of the rover on a system-by-system basis and re-optimize it for the competition tasks. On the suspension, we've looked at the travel vector for each set of wheels independently and optimized it to better absorb impacts. So on the front, you'll see our front set of A-arms is angled backwards by 15 degrees and our middle and rear sets by 10 degrees. We've been able to achieve a 20% weight reduction in the suspension by looking at each individual A-arm and optimizing it for its particular loads and use case. We've been able to further amplify this effect by precision machining the A-arms instead of water jetting them like we did last year. I would say the most exciting part of the suspension this year is our custom-made gas springs. We've been able to custom design and manufacture variable force gas springs that are going to allow us to optimize the rover's suspension task by task as we go through competition. The backbone of the frame is the skid plate, which is a carbon fiber and Kevlar layup that bears most of the loads of the rover. We've moved the battery to the bottom of the frame to lower our center of gravity and increase the stability of the rover. But we've designed a custom enclosure to house the batteries such that it's easily removable so we can service it at any time in a matter of moments. We've also completely re-examined how we mount antennas on the rover. We've implemented a modular antenna mounting system this year that will allow us to mount our antennas up to 10 feet above the rover. For our robotic arm, we've stuck with 6 degrees of freedom and our tested and proven differential gear drivetrain. However, we've increased the payload capacity to 10 pounds and increased the reach of the arm to 36 inches. In order to do this, we've looked at each individual joint on the robotic arm and optimized its speed and torque parameters for the specific load cases of competition. This year, we've been able to reduce the weight of the robotic arm to about 16 pounds by making use of, again, 3-axis CNC machining, but also designing our bicep to be a very custom organic carbon fiber shape. We've implemented automatic tool changing on the robotic arm to allow the rover to make use of many different end effectors in a given task. We've completely redesigned the gripper to make use of a larger motor, allowing the gripper to actuate in under 3.5 seconds and lift objects of up to 20 pounds in weight. We've completely redesigned the wheel bowls to be more flexible and lighter weight, allowing the rover to better absorb impacts with the ground. The wheels are made of alternating layers of carbon fiber and Kevlar with polycarbonate blades affixed to the edges of the bowls to dig into the ground and increase traction. We've also added polycarbonate caps to specific portions of the wheel to decrease the amount of wear that they experience during testing and competition.
Our design goal for our rover Zenith in telemetry is a platform for inexpensive, modular, robotic devices to help assist colonists. The rover as a suite of individual devices in a networked ecosystem gives many examples of devices such as an arm control module, a drive control module, a sensor hub module. Any number of our command control base stations, our PC software, may talk to any number of devices, our rover side robotic embedded systems. Our base station application software is codenamed RED for Rover Engagement Display. When RED is loaded, the control center is the first object initialized for any instance of RED. The control center is then responsible to continue to load the RED modules. RED is separated into modules, each with a separate responsibility. An example of a module could be our networking system, our GPS map, our PTZ camera control, our science control, or any other of a number of control and telemetry systems. We can have as many instances of RED running anywhere we want as it's a uplifted C# application. A data router object is what provides the messaging between the various modules of RED and the various devices on Rover. Ubiquiti makes a product called the Ubiquiti Rocket, which is a 900 megahertz MIMO IP Ethernet bridge. Basically, this is a radio that transfers internet traffic through the airwaves at a good, long-range, low control frequency. The Ubiquity rocket is between 902 and 928 megahertz, and we utilize about a 5 megahertz bandwidth. It's IP transparent, and it gives anywhere from 10 to 150 megabit per second data rates depending upon location. Our sensor board includes a custom GPS PCB and our own software to read the NMEA messages and broadcast them back to the base station GPS module in any instance of red that is subscribed to our GPS telemetry message. The sensor board also contains a IMU inertial measurement unit that deals with acceleration, altitude, pitch, roll, and yaw. In this way, we have a Google map of the terrain, and we can drop waypoints, and we can map Rover's progress as we move across the field, as well as input the hard coordinates of a astronaut or tool or anything that we would like to go find.
So our goals with the battery pack this year were to improve durability, the ease of manufacturing, and its form factor. The battery this year is similar in size to our battery last year and has similar power requirements. The pack is comprised of 8 modules in series, each with 10 cells in parallel. The pack operates from about 27 volts to 33.6 volts and can output up to 200 amps continuous current. The pack can also be charged at up to 40 amps. Our goals of the battery management system this year are to improve reliability and to monitor the state of health of the battery pack. The BMS monitors the cell voltages of each module in the pack and also monitors the overall pack voltage. The BMS also monitors the pack current out to the power board, as well as the temperature of the pack itself. The BMS also acts as an on-off switch for the rover and can support cooling fans to cool our battery pack down. Our power board is similar to last year's system and takes input of pack voltage up to about 34 volts. The power board outputs 5 volts at 20 amps and 12 volts at up to 40 amps. The power board also outputs pack voltage at up to 30 amps per channel. The power board will be mounted in the battery box and connects to our power patch panel as well. This year we went with an off-the-shelf solution to controlling our motors. We went with the Robotech MBL 1660s, which can output 120 amps at 60 volts.
The objective of the science team is to efficiently collect and analyze a soil sample. The samples that we're obtaining are from locations of geological significance. Sites for selection include mud cracks, washes, and cryptobiotic soil, which are indicative of water and possible microbes that have lived there. Major improvements this year include the light-proof box for our sample bay by ProtoCase, our ability to remove topsoil from our soil sample, and also the sensor arrays in both our drill sheath and our sensor sheath to observe the properties of the soil at our drill site. The sensors that we've added this year include temperature, moisture, and a borescope. Our drill has the capability of returning 6 samples to our sample carousel, about 30 grams each. Sample collection is made possible by a steep auger drill bit and a carbon fiber housing surrounding the drill bit. With our improved drill and sample bay system, we are able to reduce the amount of contamination in our soil samples. The sample bay on Zenith this year has the new iteration of this Raman fluorescence spectrometer, and we also have a multi-sample rotating carousel. This sample carousel is housed in a light-proof box, which also has a funnel for collecting the sample from the drill. After collecting our soil sample, we'll bring it back to the base station for analysis using a nitrate testing kit, a barium chloride test, a potassium permanganate test, and a hydrochloric acid test, which is looking for carbonates in the soil, which is indicative of possible marine life. The nitrate testing kit is looking for nitrates which can be present in amino acids and DNA. Using barium chloride, we're looking for barium sulfate and specifically any sulfates that may be present in our soil sample. The potassium permanganate experiment is looking for sugars that microbes will use for creating energy.
Every decision this year was made with competition in mind. In terms of science, this meant choosing non-destructive experiments that complement each other to give us a better idea if life is present or was once present. On the mechanical side, this can be seen in the wheels, which were specifically designed for the terrain traversing task. They can absorb the impacts that the rover will face going over the rock bed or down the meter drop, but they can also allow us to climb the really steep inclines that we will encounter. We've also added a camera gimbal and drop bays this year. The drop bays will allow us to deliver tools quickly in the astronaut assistance task, and the camera gimbal will allow us to survey the field in all tasks.
Our team functions like a small engineering firm run by a 4-person executive board. Our chief financial officer deals with procurement, inventory, and fundraising. Our chief administrative officer deals with inter-team communication, and our chief executive officer deals with external team communication. Meanwhile, our chief technology officer serves as the project manager for this year's rover. Under the chief technology officer, we have 4 technical sub-teams: power, telemetry controls, science, and mechanical, that all deal with different systems on the rover. In addition to those 4 technical sub-teams, we also have our public relations and outreach committee that's responsible for communication to the rest of the world about the team. In order to meet the University Rover Challenge's guidelines of $15,000, the team has maintained an accurate bill of materials and on-rover budget for the entire year. However, our operating budget is upwards of $35,000, raised through a variety of sources, including corporate sponsorships, friends and family donations, and university support. The team schedule this year consisted of 4 main phases. Our first phase, the design phase, ended with our team's critical design review. Our second phase, operation, consisted of obtaining and fabricating all of the systems needed for our rover. In the third phase, verification, we test and verify all of our systems, ending in the team's rover reveal. Our fourth phase, execution, will commence at the University Rover Challenge. In all we do, the Mars Rover design team constantly pushes the boundaries of engineering. We are more than just a team, we're a family. One team, one vision. We are the Mars Rover design team.
Today, tomorrow.